Hello, welcome for week 2 of our plane and spherical trigonometry class. Our topic for this week is special triangles. The course outcome is still CO1, solve problems related to plane right triangles. And the learning outcomes for this week are LO 1.3 and LO 1.4. Discuss the characteristics of special triangles and solve problems involving special triangles. Recognizing special right triangles can provide a shortcut when determining unknown measures of the triangle. A special right triangle is a right triangle whose sides are in a particular ratio called the Pythagorean triples. You can also use the Pythagorean theorem if you can see that it is a special triangle. It can save you some calculations. Now try this speed solving challenge. Try to solve this question as fast as you can. Try to record the time that you started and the time you ended solving to see how many seconds or minutes you spent solving this question. Now try to solve this problem without using a calculator. Just write your answers and solutions on paper. The question is, in the right triangle shown below, what is the length of the hypotenuse if the sides are 15 kilometers and 36 kilometers long? Take note of the time you started solving and the time that you finished. Again, try not to use the calculator. To start off our discussion for this week, we are going to cover two types of special right triangles. One of which is the angle-based special right triangle, and the second is the side-based special right triangle. A special right triangle is a right triangle with some regular features that makes calculations on the triangle easier, or for which simple formulas exist. For example, a right triangle may have angles that form simple relationships such as 45, 45, 90. This is called an angle-based right triangle. On the other hand, a side-based right triangle is one in which the lengths of the sides form ratios of whole numbers such as 3:4:5, or of other special numbers such as the golden ratio. Knowing the relationships of the angles or ratios of sides of these special right triangles allows one to quickly calculate various lengths in geometric problems without resorting to more advanced methods. You can even solve them without using a calculator. Angle-based special right triangles are specified by the relationships of the angles of which the triangle is composed. The angles of these triangles are such that the larger right angle, which is 90 degrees or pi over 2 radians, is equal to the sum of the other two angles. The side lengths are generally deduced from the basis of the unit circle or other geometric methods. This approach may be used to rapidly reproduce the values of trigonometric functions for the angles 30 degrees, 45 degrees, and 60 degrees. This is an example of an angle-based special right triangle. This is a 45 degree, 45 degree, 90 degree triangle, or a 45, 45, 90 triangle. In plane geometry, constructing the diagonal of a square results in a triangle whose three angles are in the ratio 1:1 is to square root of 2. As you can see in this 45, 45, 90 triangle, the length of the sides have a ratio of 1 is to 1 is to square root of 2. Hence, the angles respectively measure 45 degrees or pi over 4, or two 45-degree angles and one 90-degree angle, which is equal to pi over 2. The sides in this triangle are in the ratio 1 is to 1 is to square root of 2, which follows immediately from the Pythagorean theorem. Of all right triangles, the 45-45 90-degree triangle has the smallest ratio of the hypotenuse to the sum of the legs, namely square root of 2 over 2, and the greatest ratio of the altitude from the hypotenuse to the sum of the legs, namely square root of 2 over 4. So if your leg has a measure of 2, then the other leg has a measure of 2, and the hypotenuse would be 2 square root of 2, or 2 times square root of 2. That's just for an example. I'll give you another example later. Our second example for an angle-based special right triangle is the 30, 60, 90-degree triangle. This is a triangle whose three angles are in the ratio 1 is to 2 is to 3, respectively measured as 30, 60, and 90 degrees, or pi over 6, pi over 3, and pi over 2. The sides are in the ratio of 1 is to square root of 3 is to 2. For example, if the side opposite to the 30-degree angle is equal to 2, then the side opposite to the 60-degree angle would be equal to 2 square root of 3, or 2 times square root of 3, and the hypotenuse would be equal to 4. The second type of special right triangle is the side-based special right triangle. These are right triangles whose sides are of integer lengths, with the sides collectively known as Pythagorean triples, possess angles that cannot all be rational numbers of degrees. They are most useful in that they may be easily remembered, and any multiple of the sides produces the same relationship. There are several Pythagorean triples which are well known, including those with sides in the ratio 3 is to 4 is to 5, 5 is to 12 is to 13, 8 is to 15 is to 17, 7 is to 24 is to 25, and 9 is to 40 is to 41. The 3 is to 4 is to 5, or 3, 4, 5 triangles are the only right triangles with edges in arithmetic progression. Triangles based on Pythagorean triples are Heronian, meaning they have an integer area as well as integer sides. What are Pythagorean triples? Any group of three integer values that satisfy the equation a squared plus b squared is equal to c squared is called a Pythagorean triple. Any triangle that has sides that form a Pythagorean triple must be a right triangle. Some examples of Pythagorean triples are triangles that are 3, 4, 5 triangles and 5, 12, 13 triangles. So what is a 3, 4, 5 triangle? A 3, 4, 5 triangle is a right triangle whose lengths are in the ratio of 3, 4, 5. When you are given the lengths of two sides of a right triangle, check the ratio of the lengths to see if it fits the 3, 4, 5 ratio. So the length of the side, the shortest side is 3, the next is 4, and the hypotenuse is 5. So for example, if you are given two sides, the shortest side is 6, the next is 8, so you can guess that the hypotenuse is equal to 10. This is another example, 27, 36, and 45. How do you solve for 45? If this is unknown, simply divide 27 divided by 3, that's 9. So 9 will be your multiplier for all sides of a 3, 4, 5 triangle. So correspondingly, 4 times 9 is equal to 36, and 5 times 9 is equal to 45. In this second triangle, the multiplier is 6 divided by 3, 2. So 4 times 2 is 8, and 5 times 2 is 10. What is a 5, 12, 13 triangle? A 5, 12, 13 triangle is a right-angled triangle whose lengths are in the ratio 5 is to 12 is to 13. It is another example of a special right triangle with a Pythagorean triple. For example, we can see that the shortest side has a measure of 5. The second longest side has a measure of 12, and the hypotenuse is 13. So similarly, a 5, 12, 13 triangle with the shortest side with a measure of 10 will have the second longest side with a measure of 24 and a hypotenuse of 26. We can see that the multiplier is 2 to get that ratio. This third triangle, we can observe that it has a multiplier of 3 because, for example, 36 divided by 12 is equal to 3. So to get the other sides, we simply multiply 5 times 3 is equal to 15, and 13 times 3 is equal to 39. Now let's try to solve these following sample problems so you can apply what you have learned so far. The first question is, find the length of the hypotenuse of a right triangle if the lengths of the other two sides are both 3 meters. So let's try to draw a right triangle, and both of the two sides other than the hypotenuse has a measure of 3 meters. So they are equal in length. So if the sides are both 3 meters, then it would follow that the angles opposite to the sides are also equal. That could only mean that this is a 45, 45, 45, 90 triangle. So the question is, if both sides are 3 meters in length, how long, or what is the length of the hypotenuse? So this is obviously a 45, 45, 90 triangle, and it would follow the ratio for the sides would follow 1 is to 1 is to square root of 2. So the multiplier would be 3 divided by 1, that's equal to 3. So we simply multiply 1 times 3 is equal to 3. 1 times 3 is equal to 3 meters. Square root of 2 times 3 is equal to 3 square root of 2 meters. So that's our answer for the hypotenuse. The length of the hypotenuse is equal to 3 square root of 2 meters. We were able to solve it without using a calculator or using any of the equations and formulas. Our next example find the lengths of the other two sides of a right triangle if the length of the hypotenuse is 8 inches and one of the angles is 30 degrees. Since one of the angles is 30 degrees and this is a right triangle, then it could only mean that this is a 30, 60, 90 triangle. Because if one angle is 30, then it is a right triangle, so the other one would be 90. 180 minus 90 minus 30. The remaining angle is 60. So the given is the hypotenuse is 8 inches. The hypotenuse is the longest side. The side opposite the 90-degree angle. So the ratio for a 30, 60, 90 triangle follows with 1 is to square root of 3 is to 2. That is 1 for the side opposite to the 30-degree angle, and square root of 3 to the side opposite to the 60-degree angle, and 2 to the side opposite to the 90-degree angle. So let's solve for the multiplier. Since the given is 8, so 8 divided by 2 is equal to 4. So we simply multiply the sides by 4. So 1 times 4 is equal to 4. The shortest side is equal to 4 inches. The other side is equal to square root of 3 times 4. So that's equal to 4 square root of 3 inches. So we were able to solve for the two sides without using a calculator and without using any formula or equation. The shortest side, or the measure of the side opposite the 30-degree angle, the measure of the length of the side opposite to the 30-degree angle is equal to 4 inches, and the other leg, the measure of the side opposite to the 60-degree angle, is equal to 4 square root of 3 inches. So that's the answer for this question. Our third example, find the lengths of the other two sides of a 5, 12, 13 right triangle if the length of the hypotenuse is 117 feet. So it's directly stated in the problem that this is a 5, 12, 13 triangle, but it's just a larger version because the hypotenuse is 117 feet long. So the question is, if the hypotenuse, which is opposite to the 90-degree angle, is equal to 117, how long are the other two sides? So that's easy. Since this is a 5, 12, 13 right triangle, it follows the ratio for the sides. The length of the sides follow the ratio of 5 is to 12 is to 13. So you simply divide 117 divided by 13. So let's try 13 times 10 is 130. So 13 times 8 is 80, 24, 104. So it's not 8. 13 times 9 is 90 plus 27, that's 117. So our multiplier is 9. Simply multiply 5 times 9 is equal to 45. And 12 times 9 is equal to 108 feet. So we have solved both of the other sides without using a calculator or any other special formula. The shortest side has a length equal to 45 feet. The second side has a length equal to 108 feet. So as you can see, we were able to solve for the lengths of the sides without using a calculator, just using our knowledge in special triangles. Now let's see if you can apply what you have learned so far. In your notebook, try to solve this exercise problem. The question is, in the figure given below, the initial course AD of a ship crosses an area of shallow water at sea. So obviously it has to avoid that shallow area to avoid the risk of grounding. In order to avoid the area, the ship turned through an angle 60 degrees at A. So the ship turns 60 degrees starboard side and measured 0.6 nautical miles to a point C. So it traveled 0.6 nautical miles until it reached point C. The ship then turned through an angle of 90 degrees or perpendicular at C and continued through the course CB. If point B is on course AD, so if point B is right back on its original projected course, how far must the ship travel from C to reach B? So how far is the distance from point C to point B? Try to answer this question without using a calculator. Now to close, let's try to solve another speed solving challenge. This is question number 2. Again, take note of the time that you started answering and the time you finished answering. You answer this question without using a calculator. Just use your scratch paper and the knowledge that you have learned in this week's discussion. So the question is, in the right triangle shown below, what is the length of the hypotenuse if the sides are 20 kilometers and 48 kilometers long? Our evaluation for this week: at the end of this week, you should be able to solve problems involving special triangles. Just go to week 2 classwork posted in the online classroom for NGEZ 9, plane and spherical trigonometry. So I'll see you next week. Next week's topic is course and bearing problems involving plane right triangles.